semicolon, comma. Okay, let's try it out. You should be seeing my screen. Okay, it's loading some symbols that might. Okay, that is it. Strichpunkt B. Up. Comma B. But that's not the binary representation. That is just maybe it only works with integers. Yeah. So with floating points it will not work because it's supposed to be kind of meaningless, but apparently it works if you yeah, that's nice. Now you need to write comma B. And I guess if you write comma H it will be hexadecimal. And if you write comma D it probably will be decimal, yes. You could also write comma O for octal. No. That's also binary. Why is O also binary? Ah, that must be octal. It just looks for some reason. And we can change the values. Yeah, it's octal. So O is for octal. That's nice. I didn't know that this is possible with the UI. And let's see if we can use that. Because here it just takes whatever you set as a. So normally it's hex or decimal based on the position of the switch up there. But let's see if this can be used here also. Oops, comma B. It can. That's nice. Okay, so very cool. So you can apparently even use this comma notation in the imminent window. That's useful. That's mighty useful. Okay, any more questions? Well, you have a floating point number as input, so it's a variable of type float, and as output we expect 3 variables of type integer. You don't need to display it or anything. You just need to produce the right output. Well, that's the point. The representation is different, so I mean, that's why I gave you this website. You can check your output against what this website produces as an output, and if it's the same, then it's right, and if it's not the same, then it's probably wrong. Because the link is in the homework and in the source code, and then here you can just enter some floating point number 1, 2, 3.567, 8. Press enter, and then it shows you which bits are set. So if we make it negative, you just change the sign bit. So we can also the other way around just create a number by switching bits here. So you can see which effect each of those bits has. Well, after splitting, you should have one variable which is only 0 or 1, another variable which represents this portion, and another variable which represents this portion. And always moved such that the bit here is the least significant bit. So this thing here you need to shift to the right by, I don't know, however many bits these are. I think yeah. You mean for a practical use case? Well, that's just up to your imagination. I mean, normally you would not want to uh, save an integer that started off as a bigger one as a shorter one, because then if you would happen to have numbers which are longer, then you would lose data, of course. So you would then store the wrong number. So you would not use this directly this way. What you could do is you could devise a format where you, let's say you only use positive numbers, but you would then use the first bit as a flag, which would indicate how many bits the file is your number has. So let's make some notepad. So for example, you would you could represent values from 0 to 127, and so it would be like first bit that would be a f, and then you have 1 2 3 4 5 6 7 bits, and those bits can represent a value from this range, while your flag tells whether this is all or whether there is another bit attached. So if this one would be 1, then it would tell you that there is 1 2 3 4 5 6 7 8. Is that 8? No, one is missing. 8 more bits. So this way you could, for example, use one flag to indicate how many more bits they are. So when you write it to file, you only need to write 1 byte if the flag is not set, but if the flag is set, then you write 2 bytes. And of course the assumption is that in principle you could also reserve two bits. I mean, it depends how easy you want the passing to, because one approach would be to have 2 bits reserved from the get-go, and then here you can only go up to, what was it, 63. But 2 bits, that gives you already 0, 1, 2, and 3, so you have 4 values. So you could have, so 0, 0 would mean it's just 1 byte, 1 would mean it's 2 byte, and 3 would mean, I mean, you could go with 3 bytes as an additional sort of type, but that would be uncustomary. Usually you try to go always with pass of 2, so the next higher value you would have would be something that goes is this enough? Yes, something like this. And so you can have 0 till 120, 0 till 63. The next one is, I need a calculator for that. I think it will be like 15 something something something. 2 to the power of how many bits? 2 bits, 13. That is, okay, that's 16. 0 till 16 3 8 4. And if you set both of them and use the additional field, that would be 0 to 2 to the power of 30. That would be like a billion or something. Too lazy to type. It's this number. So this way, if you know that for whatever application you're using this number, it will never exceed a billion, then you could, if you expect that usually the numbers will be shorter, use those. And in principle, then you could even use, like, because we have four values, so we could add one more letter. V, and then just have this to be a 64-bit number. I'm too lazy to type the right amount of V's. But then you could go, that's a big number, 2 to the power of 62, which for pretty much all practical application and purposes is more than enough. So this way you could save some space in your file format if you are trying to write something for a microcontroller where every single bit counts. But more common applications, what you also could do is that you could, for example, have different flags. So you could define that the first, let's write down something. It's too much typing. Let's just maybe reuse. We don't need an example. The idea is that you could, for example, say that the first byte of your 32-bit integer has one meaning, or that you even use a single bits, like we have seen here. flags where you could set here set and clear flag. So you could have a lot of parameters or properties which you can enable or disable, whether it's a 1 or a 0. You could also assign 2 bits per flag, so that if both bits are 0, it means the flag is a default. If 1 bit is set, it means it's enabled. If the other bit is set, it means it's explicitly disabled. And if both are set, then you have an undefined state, or you come up with some other application. But this use of single bits or just single pairs of bits for flags is quite common all around the operating system. So, for example, when you create processes, then you have a couple of flags which you can specify, which then tell you whether the process will be running outright or will be suspended, and you can change other parameters as well. And what you can of course do is that you define that the lower 16 bits of your 32-bit double word are a field for flags, while the upper 2 individual bytes will be, let's say, I don't know, priority, CPU priority, and something else, IO priority for the other one, for example. So if you either want to save the amount of parameters you are passing into a function, which might be nice for people. So you would not want to write a function which has 100 parameters, which where you just say true, false, true, false, true, false, because that's just tedious to program. You would want, in this case, to come up with some nice scheme of flags which can be specified, or if you don't want, then you just write a 0 for this parameter if you don't need to set anything there, and this way you can create a much nicer API for your users. Yeah, so it's quite useful. So in principle, even more exercises in bit shifts and bit manipulations would not be completely wrong. Mm-hmm. Mm-hmm. Any more questions? No more questions? Okay. Yeah, since we are 15 minutes in anyways, then I guess we are just 23 people. That's okay. So let's continue with our variables. So where did we arrive at the end here? So in my initial planning, it was kind of intended to now take a look on flow control and then on pointers, but I think it might be more useful if we first do the pointers and then take a look on flow control. I think both should be fit in one lecture anyways. So as you have seen with this line, which I have not explained the last time, what we basically do here is we force the compiler to create code which will take a memory location of a double, so of a 64-bit floating point number, which has this IEEE something 574 format, and then just copy this memory onto a memory location which yes, of course. Okay, maybe I can get rid of this side window. Yeah, that's better. Anything else I can get rid of? Yeah, that's fine, I guess. This line should be here. Yeah, that should be. Maybe I can turn off here the toolbar somehow, somewhere. View. Oh, I could go full screen. That is somewhat nice if I disable this. Oh no, I can no longer access it because my mouse goes to the to the other screen. No, it works somehow. Yeah, but that should be good enough. Now you just see the screen without useless things on the sides. So where was I? Yes. So we are forcing the compiler to generate code which will take this double number and copy it into a memory location which is supposed, according to the rest of our program code, to just contain a integer number. So the length is fine, so the number will fit, but of course the representation is completely wrong. And what we are doing here is we are using using pointers and are using a typecast. So about typecast, I already said that earlier, that in principle you can tell the compiler explicitly if you want a conversion, although this normally also works without, just that if you don't specify it and you are doing a conversion where the compiler sees that the result may be considered a loss of data, which is often the case when casting from a double to just a normal integer, then it will complain. But if you tell it tell the compiler explicitly that you want to do it, it will just accept it without any complaints. But going down to this line, so what we are doing here is first we create a pointer, so we could write this line down in more lines. So let's comment this out. So a pointer basically is an integer number. The length of this number is always platform dependent, and so for normal x86 programs, operating systems, CPUs, it's 32-bit. For x64 it's 64-bit, and for other architectures usually this will be noted somewhere. So like normal ARM is 32-bit. Now with ARM 8 you have the 64-bit version, so any CPU that's ARM 8 or newer can run a 64-bit code. So in this mode it is 64-bit, and if you would run some very old x68 CPU, you may have encountered like DOS or something there. You have a 16-bit pointer length, which is very limiting. So a 16-bit pointer can address only values from, so let's write it down, 16-bit, obviously 0 till 6, and then something. I can write it down in hex that I know. Oops, it's not typing. The hex values are easy. XFFFF. That's like, I mean, for this one we can take this and get a Taschenrechner to convert this for us. So this is this. For the other ones, it doesn't matter. Then you can have 32-bit. Then you can address up to 4 GB. On Windows there are certain on Windows there are certain limitations to this, which I will explain shortly. And in 64-bit you have in principle, it's a really big number. I think it's a sextillion or 16 sextillion or something like that. It's really big. So realistically, we will not be able anytime soon to use anything close. So get a computer with anything close to 64-bit. So it can be assumed for the foreseeable future that probably there will never be a 128-bit CPU with regard to addressing. It doesn't seem to be realistic to create something with so much memory currently. And if we would go to some artificially grown, well, I mean, when you think about the human brain, we obviously have maybe much more addresses there, but probably if you would create something that is not based on modern lithographic process, but to get this much memory, you would need to make something that grows itself, basically, because doing it in time sequentially would simply not be feasible. And I think for such cases the design would be somehow completely different, so it's not even I guess feasible to think in this types. It would be just maybe maybe what you could imagine it would be more structured like a supercomputer, where you have normally just computing modules, which each of them has a lot of memory, but then they cannot address each other's memory arbitrarily, because then the connection time between them would be far too large. So what you have there in supercomputers is that you have individual compute units which can access all the same memory, and then they are connected to the next one and the next one, and the operations are scheduled such that that basically just every part does its job, and then the data are in the end merged. So it might be said that probably we'll never see an architecture with more than 64 address bits, but well, who knows? Maybe I'm wrong. Yes, so things to be noted about this pointer ranges. As said, this is extremely small, and even DOS could already address up to a megabyte of memory, which is I think it's 20 bits. And the way they did it was through the use of additional registers. So while your pointer could only point onto something from this range, you could have multiple of these ranges, one after the other, and you had a separate register, a so-called segment register, where you could tell the CPU which range you are currently interested in. So obviously this made for a rather convoluted code sometimes, but when those things are generated by a compiler, as you as a human don't really need to care that much, because the compiler will do this required operations for you. But aside from DOS, any more modern operating system, whether Linux, Mac, Windows, or what else, there is not much else, BSD, which basically is the base for Apple's operating system. So Apple is not really like anything new. They just have a BSD kernel and then put just some nice UI on top of it. So all of those operate with a so-called flat memory model. This means that you have a pointer, this pointer points to something, and this is all the memory you can address. This is the reason why many 32-bit operating systems in the old days, where you still had 32-bit operating systems, were limited to only usually 2 to 4 gigabytes of memory. There are in fact two limitations. One limitation is with regard to the physical addressing. So on modern computers, unlike in the good old days of DOS, you do not use physical addresses to address memory. So a physical address is basically the offset in memory, which really tells you the memory cell number 124 contains the byte you are interested in. So this is a physical address, and you can of course nowadays still run into physical address when you're writing programs, for example, for a microcontroller like an Arduino or something comparatively simple. Those things don't have any memory protection, any memory management. You just are addressing the raw memory as is. But in anything more complicated, for example, in things like a Raspberry Pi, there you have a full memory management unit, which is a part of the CPU which allows you to use so-called virtual addresses. A virtual address basically can be understood as a addressing range or address space that is in a way exclusive to one process on the system. So the idea is on such systems that every process will basically just see its own memory, and another process can have in the numerically same memory location completely different things, and this then is translated by the CPU from these relative addresses to physical addresses for every process individually. This translation, of course, is not done like on every like byte by byte basis, but it is done in so-called pages. So a page is normally 4 kilobyte large. In principle, you could have different page sizes, but this is not something that would be commonly used. And the idea is that any page from the physical address range can be mapped into an arbitrary location, aligned to a page boundary in the virtual address space of a process. So this way, every process can get its completely own memory and be happy with it. So whatever it does, it cannot affect other processes. This is of course to some extent limited, so you need a way for the process to interact with the operating system, or maybe if you want even to interact with other processes. And normally in modern operating systems this is done such that the whole available address space of, in the case of 32-bit 4 gigabyte, is split in two segments. You have the low address range for the first 2 gigabyte of memory, which is exclusive per program, and there the memory for every program is just whatever the program put there. And the upper address range, upper to 2 gigabytes of memory, are in principle the same for all the processes, but of course they don't really have access to most of this memory. So this memory is used by the operating system kernel. And the idea simply is that you want to know that whatever in this address range you might want to use or to expose to the application, that you know that you will never run into a situation of, oh, I already gave this address range to the application for another purpose, because that would be a problem. So the simple solution is simply that you just say this whole upper range is reserved, and even the application for most of the part cannot access anything there. If I need to make something from the accessible to the application, then I can do it. And in fact, on the very oldest operating systems, you had an option, like on Windows XP and Server 2003, to change this split from a 2 and 2, so from a 1-to-1 split, to a 3-to-1 split. So this way you could give 3 gigabytes of memory, of address space, I should rather say, to an application, and keep only 1 gigabyte of address space to the operating system. This was sometimes useful, and what you could also do in this on 32-bit machines is that you could use so-called physical address extension, which basically was to use the techniques from DOS, where you had additional registers which then specified which range you are really using. So you could have, in principle, your Windows Server 2003 run with 16 gigabytes of memory even, but every application on the system was still limited to only the 2 or 3 gigabyte that the address space allowed for, because it was not really supposed to switch address spaces within the application. But what you could do is, you could, since you are assigning the physical addresses to some virtual addresses within the application's address space, if this assignment mechanic was extended by additional bits, you could then address more than the 4 gigabyte of memory which you normally could address. This, as far as I know, is not longer in any way in the 64-bit architecture intended to be used. And as said, it probably is not necessary, because you have such a huge address space that this is not a problem. One thing that you could run into as a problem with with a 32-bit address space is that if you place many things in your address space, and at some point you say, okay, now I want 1 gigabyte of memory in consecutive addresses, then you could get a out of memory error, even if in principle this amount of memory would be free, but it was not longer free in your address space in one continuous block. Of course, on 64-bit, given that you have zillions of addresses available, you will most likely never run into such a problem, at least not when operating within an application. You might run into issues if you would want to allocate a large amount of physical memory, which is aligned really like in one chunk. Why would you want to do that? Probably you wouldn't, but in specialized cases, if you would have some sort of data acquisition hardware, you might want to, which is basically capable of writing into physical memory directly. So this is called DMA, direct memory access. You might want to give a very large buffer to your hardware, and then within the driver for the hardware, you would need to physically allocate a very large block in one piece. That said, if the hardware is designed well, it should not need the buffer memory to really be in one piece. Ideally, you should be able to tell your hardware just a couple of ranges, and this way it's much easier to allocate memory. Or the typical implementations might not even be like that. You can just give an arbitrary list, but for example, the design would be that you are just giving out the buffer in 64 megabyte or in 1 gigabyte. That would already be quite big, but in chunks of a certain size which can be used, and then you just can provide a very large list of these chunks wherever there was memory to allocate. Yeah, so much to addressing and memory. And to come back to where we started, So a pointer, as said, is just an integer in your memory somewhere which contains the address of something in memory. So if we want to create such a pointer, we can rewrite a data type, let's say double, and then we just add asterisk and then write some name for the variable. Usually it's customary to start pointer variables with a p, so let's go with pfvar. And now we want the address of this variable, and this can be get with the AND operator. So if you prepend a variable with a AND operator, it will give you not the content of the variable, but the place in memory where this variable exists. One thing that is also important to note here is that such a pointer always points on to memory. It cannot point on a register or anything like it. So it is in principle typical in your C application then that every variable will have a memory location. But of course, in the course of optimization, the compiler may decide that a certain variable might only exist in a register. So if you have all the optimizations on, then it might no longer be true that every variable will have a memory location. And or what also is possible is that the compiler says, okay, so let's do 20 operations before we save the value back to memory. And of course, this is not so bad because it makes faster since you are since you don't need to make the memory accesses. But of course, it can make the debugging more difficult if you don't have all the register states available. So when you have a live program like we have here, this usually is not a problem. Also, you will not be using optimization anywhere. But if you would have a crash dump from an application that crashed on someone else's computer and he sent it to you, hey, can you take a look on this crash dump of your program, it crashed, then there might be many informations missing, especially like register content. So that said, we can maybe run the code quickly and see how this looks. That should compile quickly. Okay, we have a breakpoint we don't need anymore. And if we take a look, then we see that it uses the load address instruction. It loads the address of, well, this is of course not the one to symbol names. Yeah. So if we have a display without symbol names, we see that here, in principle, we are just taking the RBP register content plus a offset. So every variable in our program will have a different position relatively to the stack pointer and relatively to the frame base pointer. And since we are compiling this as a debug build, then this RBP will always be available and point on the beginning of the memory used by our function. So somewhere here. With optimized code, as I mentioned last time, this base pointer might be omitted, and then instead the compiler would just use dynamically generated values for the offset from the current position of the stack pointer. But since the stack pointer can change during the function's operation, it of course means that the compiler needs to keep track of it, which it can, it's just fine. But for a human, if you would write assembler code, that would be probably a huge pain to do. This is why usually it was intended to use this base pointer instead, such that you have a fixed reference for when you are inside your function from which you can always use the same offsets. Anyhow, it loads this number into the RUX register, and then it just saves it with the move instruction to the memory location where we have our pointer variable. And if we go one step down, we see that here clear, we have some integer number, and it shows you here in brackets whatever it points to. So if you have a pointer of a type like double or whatever, then it will try to interpret the type, at least if it's a simple type that it understands. So if that would be some structure or some structures it understands also, but if it would be something like a more complex class or something like that, then it would not either not show anything, or depending on your installed extension, it might show something for that. But this is a detail. The important thing to know is that this type is really just something for the compiler, so we can also create a pointer to something that has no type. In this case, we just use the void keyword, which basically means it's a type that is not a type, or that is just not existing. Then we need a new name, so let's call it just p pointer. And this will, in this case, do the exact same assembler code, but first of all, while this still works fine, this should give us just the numerical value but no interpretation, because at this point the compiler knows, okay, this is a type I don't know, so I can tell you the exact number, but I cannot tell you anything more. And type void is in fact quite useful usually if you have functions that are operating with buffers or similar things. You would want to use type void, because then you can pass different types to the function, and then obviously the function needs to, based on other flags or just on what it is supposed to do, know what to do with this data. So for example, a function that writes or reads from a file, you could will take a pointer to type void and a size, so how much to write or how much to read. And if you have a complex structure or something like that, then then you can just tell the function how large it is, and it will just write it in one go. It doesn't care for the internal content. How structures work and so on, we will probably take a look on next week, because that's also not a small subject. But just to have said it quickly, the idea is that you can have a couple variables put together into one block of memory, such that you can address them individually and as one thing. So that's probably simplest thing how a structure could be explained. But anyhow, so going back to our pointers, the nice thing here is that we can create a pointer of anything. So if it is in memory, we can have a pointer on it. And what we can do as a next step, we can, so we don't need this one, we can create another pointer. In this time, let's do it an integer. Let's call it payvar, and then we can use the cast operator to cast from from one pointer type to another pointer type. And the operation here, in principle, we don't need this. So I mean, the compiler probably will complain if we don't have it, because this is usually, if you do it by accident, probably a sign of a bug. It's even underscoring it in red. So we have to tell the compiler we know what we are doing. This is intentional. It's fine. And then if we try to build it, we'll build it just fine. And then we will notice that both variables will still have the exact same content. So like this one is clear the memory address, and this one is the exact same memory address. As you see, they are identical, just that what it tries to interpret for us is completely different, since it's not since it's just really a blank copy. It is not in any way, shape or form have been converted. It just, if we look here into the assembler, our operation, where was it? Yeah, here it's just one move operation, load from an address, and another operation, write to an address, and that's it. But what we can do also with our variable, with our pointer, is we can access, of course, its content. So we can have our normal variable, and to access the content of a pointer, we use the asterisk operator. So this operation here will now say, take the memory pointed to by this other memory and write it to yet another memory location. So we can run this quickly. and we see here how this was implemented. So it needs a couple more instructions. So first we get to Rax, to our Rax register, the value of the pointer, so the memory address. Then in the next operation here, we just take the memory at the value pointed by Rax. Now at this point we have our double inside the Rax register, and then finally we can write it here back to another memory location. And of course those 3 lines can be just expressed with this one line. So we take the address, we convert the type, and then we dereference it to get the actual value. And this is called and this is called dereferencing. And it's just a typecast. Okay, so that's like the very first things about pointers, but of course there is more. As you have seen, we have this RBP point and RBP register, which allows us to access things on the stack. But in principle, the way this is done, there are 2 types of, well, maybe not 2 types, how to say it best, there are 2 schemes how you can access memory inside of your program. So one is the stack. So the way this starts is that you have your function, and when the operating system sets up your first thread and the entry into the function, it will allocate some memory for you and write this value, the first address of this memory into your stack pointer before it starts the function, and then you have other functions, and the stack pointer gets increased and decreased all the time. And so the thing is, I think I explained so last time, that you get like a hierarchy of which function called which, and you can only get out of this. You cannot move laterally in the stack. So the idea is basically that like and the name of a stack. So you have like a base, and you put things on it, zack, and then you can remove it only in the same order in which you removed in which it was added initially. This is very useful, of course, for functions, but if you want a very large amount of memory, that might not be that useful, or if you want to access memory randomly. So when you write applications, then it is quite often that you want to have some data blocks somewhere in memory, and then you want to access it from different functions and at different times of your program's runtime, so to say. So you have another means of accessing memory, which is called the heap, and the idea is that you can just request at any time. So the heap is implemented by your C runtime, and it is implemented in collaboration with your operating system. So there are operating system calls which you can say, hey operating system, give me this amount of memory, and the operating system will then allocate for your program this amount of memory and then give you the pointer, or it will tell you error out of memory or something like that. And then this memory within your application is managed by the C runtime, and it exposes a couple of functions that you can use to access this memory. It's called malloc and 3. And malloc is, as the name just says, for memory allocation. So it gives you a block of memory, and 3 will just then tell the operating system that you are done using this memory, and and basically that this memory can then be used for something else. So the operating system could then assign this memory to another program or to do whatever it wants with it. But on this we will take a look in one of the later lectures. Now let's continue with our pointers. So for here, I guess we can close this project, and we create a new one called pointers. Console application. Okay, so so as I said earlier, we start with some variable int my 123, and the pointer is int my. We can assign it a starting value, for example, of 0. And one thing that is also quite nice is that we can test var. We can use the size of instruction to make the compiler tell us how big a certain variable is. So if we do this, well, we should add const, then it will evaluate this already, and it gives us here the size. If we can do the same thing also for a pointer, and you see here that it is 8 byte in size. And if we would switch here to a 32-bit platform, then it would automatically go down to 4 bytes of 32-bit. This is quite useful. So size of can be used and is used very often if you have more complex data types, so that you don't need to write down a number, and if you then later change the data type. So we might decide that in integer is not enough, we need a int 64, and if you would have written somewhere in your program here just a 4 instead of size of this, then you would need to change it in all the places. So it's very customary to, when doing anything, to always use the size of whenever possible. There are of course situations where size of doesn't work, so but that we will but this we will take a look on later. So to have this all written down, just quickly add some thingies. So this we had. Yeah, okay. Another of course quite interesting thing which I have not demonstrated is that we can of course use the pointer and dereference it and assign it a value and assign the dereferenced memory a value. And now you will see when we execute this line, we will change in fact the value of my var. So now the line is not yet executed, it's waiting to execute it. And okay, maybe I should switch to decimal. So we have here our 1, 2, 3, but as soon as we execute this line, the value in our memory location in our variable has changed. This is also a very useful capability. So you can, for example, have a function to which you pass an address to something that you have defined outside, and the function can then change the content, and then you can use this to have more than one return value, for example. So if you have a function, like a mathematical function, there's always one output, but you might want actually to have multiple outputs. And while in other languages you can in fact define multiple return parameters, in C you cannot. But instead you can just pass an address and then expect the function to write to this address whatever you wanted to write to this address. It's often implemented such that if you pass as an address the value 0, you can also write null. Null is just defined as null, basically. So ideally you should never, so the operating system will never give you within a normal application a memory range that starts at 0, because the value 0 as such is reserved for basically an invalid to indicate an invalid memory. So when you are interacting with various functions that take addresses and you refer to their documentation, they will often say that if the value is 0, then nothing is done, or it ignores it. So for example, you could have, when you read from a file, let's say at reading and writing files as an example, so you would have one argument that tells you, that expects the pointer of what is to be written. This one should obviously not be null. Then you have a value that just tells the function how many bytes you want to write, and then you will get another, and then you would have a pointer where you can give a pointer on an integer variable, where your write function will then write how many bytes it has really written. So assuming the hard disk is full, you may say you want to write a few megabytes of data, and the thing may say, oh, but after 1 megabyte I ran out of memory, of disk space, I mean. So in such a scenario, the right function would usually succeed, but not entirely. So it would indicate this failure mode with a return value. But if you want to know how much it has written, you would refer to this additional parameter. And of course, normally you don't expect such situations when writing to a hard disk, so I would probably just give it 0 as a parameter and be happy. But there are other scenarios where you might in fact want to know how much was written, because usually functions to access, for example, network resources are structured very similarly to functions used to just write to files, and on some operating systems they're even the same. So you open a network socket or a file, and in both cases you just get a handle to which you then can write or read from using the same function. And of course, if it's a network connection, then you will get an error that it could only write up to a certain length, because then the network buffer was full and the data could not be sent fast enough to your recipient. But of course, if you wait then half a second or maybe a few milliseconds, then you can then write again into the buffer. So at this point, it is very important to get the feedback how much was put into the buffer, because then what you can do is you can advance your pointer and then send only the next part of your data. So that brings us directly to the next useful thing, pointer arithmetics. So we have that, yeah, well, what you can do with your variables. So until now, we only had variables like a single variable contains a single value. Even if it was a pointer, it still contains a single value. But what the compiler allows us to do is to define an array of values. So for example, an integer array, my array, and then you just tell in square brackets how many elements do you want in your array to be. And then you can of course initialize it, so you cannot write 0, that would be invalid. As you see, it's complaining. But you can use the curly brackets, and then you can write down the numbers that you want your array to contain. In principle, you can write less, so you can write just 0, which in fact will tell the thing initialize everything with zeros. You can just write a couple less. Actually, I haven't tried what it then does to the last element. Let's quickly look at. My guess it will just take the last element you gave it and then replicate it until the array is full. But I've never tried it, because no, it does actually initialize it with 0. Because if you not initialize it at all, at least historically, the content of memory should not be defined. But on modern systems, it will probably be zeroed anyways. No, actually, it's not. But I think if we go to a hex display, that will give us, yeah, it was initialized but with C's. So the idea is that if we run in the debug build, that even if we don't explicitly initialize memory, it will always fill it with a pattern that can easily be spotted. So in this case, it's always CCCCC. And if we, as I said, with this memory management, would have had this memory from the heap and would have returned it, it would override the range with I think either DD or CD, no CD, with CD values, which is a huge waste, but it helps you if you would then accidentally use this memory again after having it freed to spot that something is wrong. If it would just left the memory for the meantime unchanged, then your program could work randomly and then crash at some point when it gets changed. So this is actually useful. But if we switch to the release build, I just have to check that all the optimizations are off, because if they are not, then it will probably just remove all the variables which we are not using. So let me quickly adapt this. Optimizations, yeah, we don't want any. And let's run. Okay, what did it do? Hello. Okay, it doesn't want to tell me. It might have removed the variable still. Yeah, it completely removed it. It optimized it away entirely. So this, I'm afraid I might not be able to demonstrate it so easily. You would need to. This is already disabled. Can we do something else? Yeah, there are many settings, but I think that will not be that quick to find one to disable that. I mean, what we could of course do is just to use the variable. Oops. I don't think the compiler is smart enough to optimize only a part of it away. Yeah, well, so here, in fact, we see there is still garbage in memory. Although in principle, when you get the memory from the operating system nowadays, the idea is that it should either be that it should be zeroed or filled with garbage on purpose. Because the thing is, if the operating system gives you some memory, you use it, you write some private stuff in there, and then you close your program, the memory gets freed, and then another program on your system can say, okay, give me some memory, and then if the program would be malicious, it could just see, look, okay, what did I got? Was there something interesting? And something that starts with password double point. I should send it to my master. So to avoid such scenarios, Windows will usually not give you a memory that was used by another program without clearing it first. Although that might be limited only to certain boundaries. So like if you are a user mode application, you might still get memory of another user mode process. But if you are a program, but you will not get memory unfreed that was used before by another user or by an elevated process. So this is possible. I have not looked into the details of how they're doing it, but normally it is supposed to avoid this sort of data leaks nowadays. But of course, within your own application, you can free some memory and then reallocate it, and then you will just get some garbage that you have put there before that. So I guess the content we see here comes from such a scenario. But, going back to our debug build, as said, we can initialize it, and as said, it seems that if you initialize with any length that is non-zero, it will initialize the rest of the array with zeros for you, which is quite nice. Yes, and now the next interesting thing is, of course, how can you access such a that would probably be good to have done it in a different order. So if you want to access an array, what you are doing is just you write the name of the array, and then you can write an index in the square bracket. So we could have, for example, a int e, which would be a counter. So then we have our array at e, so at 0, and let's say we want to assign it another number, for example. And we could use, for example, the plus plus operator to then get the next one, and the next one, and the next one. So this way we will then assign 2, 4, 6, and 8 to the first 4 entries in the array. And of course we can just get a value from the array. Int my, do we have my val? No, we don't. My val. So as you may remember, the plus plus operator gives you the value. We need the plus plus here. Gives you the value of I, and then it increments it. If the plus plus would be before I, then it would give you the value of I after incrementation. So it means that here, once we are done with this line, I is pointing to the next not yet accessed index in the array. So if we run this, we will see the effect. So if we switch this to decimal, you see we assign the first values, and then here we got the value 5 out of the array. And what we also could do is that if we want to reference some position of the array later on, or if we want to we can create just a pointer. I think my PTR we already had, yeah. And in integer, but then we cannot use of course this is square brackets. What we can use is the reference operator, or the other thing that we could do to access this address basically is to use pointer arithmetics. So we write the same thing, but here we write array plus I. And for most applications, application for most use cases. A array to a type is equivalent with just a pointer on a type. So in principle, this is just a for how the language interprets it, this is just behaving like a pointer. So for example, we could assign it like this, and then use here. Okay, let's say I should be 0 again. Then we're using this, and it will do the exact same thing. But what we also can do is we can increment it by a given value. So let's say 0, 1, so 1, 2, 3, 4, 5. Let's say we make it +6. And here the compiler, since it knows the type of the array, it will not give us a value which is just the address plus the number 6, but in fact what it does in reality is something like this. So first of all, to demonstrate, actually we need to cast it on something that is only one character in size, because otherwise the thing will be too smart. And then +6 times size of int. And now the whole thing needs to be casted back to int asterisk. So when you write a line like this, or when you just anywhere write a pointer or array, it's basically the same thing. Then in reality the line increments. You can also use minus, so you could go the other way around. Of course, if you really have the array, then the other way around would be an invalid address. But for example, since we made here plus, and in this variable we then have everything that starts at 6, we could here later on make a variable that goes back by -4, and that would be fine. So you always need to ensure that you only are accessing addresses which really exist in memory, and which are not well, invalid or not allocated. The main problem here is that the only checks that really happen inside the CPU normally when you're accessing memory is whether this memory is mapped into your address space. So if you would try to add or of course if the memory is marked as read only and you try to write it, then you would also get an exception. But normally if there is a memory page allocated at the location of whatever address you are trying to access, and if you have the rights to access it, so let's say it's marked as writable and you want to write, or if it's there is, I think, no flag for you can write but not read. So basically, let's say if you just make a read access, then if the memory is there, you will succeed. But there will be no checks whether the memory you're accessing even belongs logically to the array or the pointer or whatever you wanted to access. So this is the main risk of working with pointers, that you don't have, at least on the hardware level, any checks that would ensure that your access is valid. The only thing that you have is that if you try to access something at address 0, then it will of course fail because it's defined as invalid. But besides of this, it's up to your program to not generate invalid accesses. And such type of bugs, if they occur, might be very difficult to find, because if you are writing to memory, you can write to just some random location where some other important stuff of your application is located, and your write were fine, you exited the function, and then later you do something that accesses this important stuff, and the thing is then crashing. And to find out that this happened, or rather to find out that it happened, is reasonably easy, because if you have some really strange bug where you think that's not possible, then it's very well possible, and it's probably the reason of memory corruption. But to find out what corrupted your memory, that might be really tricky. And this is one of the reasons why nowadays, wherever possible, we are trying to use to not use just raw pointers, but something called a smart pointer, which we will take a look on much later. Or where you just generally, so smart pointers and all this stuff you can only use in C++. So normal just C has none of these. there you just have to be careful what you are doing, basically. But we will, as said, take a look soon on the C++ stuff, and there we'll have all these nice fancy functionality that helps us on a programmatic level to avoid screwing up things. Now, that said, one of the mechanisms that the compiler tries to help us with memory accesses and memory management I already mentioned. So unallocated memory in a debugger will always be, at least on Windows, I'm not sure about other platforms, I have not checked that, will always be pre-filled with a given pattern, and once the memory is free, it will be pre-filled with another one. So for example, so a typical scenario where you are accessing invalid memory or memory that you should not access is that you have an array of a given length, and then you try to access it, and then you access it, and you reach the end, and then you are still accessing it and writing to it and writing to it and screwing up other things. And normally, for example, the debug heap that the Windows C runtime provides, what it will do when you ask for some memory, it will put some memory, so it will allocate a bigger block, write some markers at the beginning, then it will write the disk, give you this amount, and then it will write some other stuff. There are two expectations for this. First of all, if you just slightly exceed your array, you will not damage anything else. But the more important thing is that once you tell the C runtime that you don't longer need this small piece of memory, oh, sorry, you don't see my second hand. That was not very great. So that you don't need this part of memory, these two markers at the ends, the heap manager will actually check whether they still contain this special pattern, and if not, then it will throw you a heap corruption exception. So it will tell you, okay, you wrote farther than you were allowed to, or even worse, you wrote into a negative offset. You probably damaged more things, but this much I can already see that you damaged. And this way, some of these errors can of course be avoided, but of course this is just an aid. It will not solve any possible memory corruption issue. So it's just usually good to use good practices with pointers to always check whether you have enough space left in your array. One thing that is to be said about arrays that is important. So as I mentioned, you can just assign an array to a pointer. So, but let's do that quickly here also. One. But if you go with this line that we had here, you will see that even though mostly an array and a pointer behave the same, they don't behave the same with regard to if they are fed into the size of operation. Because if we feed the array to size of, it will give us the size of the whole array in bytes. So really nice. But if we feed the pointer, it will just give us the size of the pointer. And the reason simply is that the pointer is just the address. It doesn't have any property that it would in any way tell the computer how much memory there could be. And this is probably something, in my experience at least, this is a mistake that can easily happen, that you try to get to use size of, but then you need to remember that this only will work if it is really the array that you are getting the size, which you are getting the size of, and not longer the pointer. If you would be using a smart pointer or some sort of array container, then it would have, of course, the pointer itself and additional fields, which would then contain, like, for example, the size of the whole thing. So we'll take a look on that once we arrive at C++. But for now, yeah? Sure. Yes. Yes, the pointer is just a pointer. So the best thing to see it is if we probably take a look how to do it. let's make a test case. So we already have our pointer here. We don't care for the sizes, and now we just try to access and change the first entry in both of cases. So let's see, 0 is equals, I don't know, 1, 2, 3. And then again for our pointer, 0 is also equal to 1, 2, 3. And then we just take a look on how these two are implemented by the compiler. Oops. I already have, okay, sure, I have a test one. It should be called test2. That's an annoying thing about writing such a demo code, that you always want to use test something, and then sometimes you might not have okay, so is the debug with yes, so move x. Why is it doing that? Interesting. Anyhow, so first it just puts the number 4, I'm not sure why, into the args register. Then it multiplies. Okay, so this will be the position inside, so from where our array. I know why. Okay, so this will be. Can I comment it? I cannot comment it. This will be the size of how many elements are, so how large and a single array element is. So it puts the size of the element into one register. Then it makes the multiplication. So in this case by 0, since we are accessing the first one. So it generates the offset from the array base. So it generates the position from the start, from the start of our array where we want to access it. Maybe I should use here a different number to make it more demo-like. Let's go with the number 2. Okay, so it generates this. So if we oops, that was one too much. One thing about this single step buttons, if this window has focus, it will step by line, but if this window has focus, it will step by instruction. So in this point we have in our args register the number 8, which is correct, which is the offset. And then you see that here it takes the base pointer plus the position of the array, and then plus where it knows that on the stack this array starts. The order might not be the most intuitive, but this is what it is doing. And if we, so in theory for the program, whether this is an array or 10 variables, one after the other, after the other, after the other, it's in memory, it's allocated kind of the same way. There is no memory location which was explicitly contain this address yet. But if we do this, so if we create a point, copy this address to a pointer, which it does here with just loading the address, then if you see the implementation, it will need to do it differently. So it also calculates the offset the same way, but then it needs to first get into another register the address of our the value of our this. So if we look on this here reference, we get an address, and RBP from this should have the same value. So that's not in hex. We want to see it in hex. Yep. So you see it first writes into an additional register the value of our pointer, and then it does and then it basically operates differently, because now so here it needed the base pointer of the stack plus the right offset to generate the address of the first entry in the array, and then to this it adds the offset from the array, while here it loads the exact address where the array starts from another memory location, and then just adds to it the position, the offset inside the array. And in both cases then it assigns our 1, 2, 3 number. So if when you make the size of operation, then the compiler just looks, okay, how much it was, and it can give you the answer. While if you make size of of this, it only can give you the size of the memory block. So size of basically just gives you the size of the memory block that is allocated on the stack, or that it will be needed, because you could use size of also with something that is not allocated. You can also write a type, so you could write size of int, but then of course the result will be just 4. But you can also use it with more advanced types. But if you are using it with variables, it will just really look how much was used for this. So this array, as said, is like a helper. So the compiler does not create anything that would represent this array as an address. It just knows internally the array starts at index such and such, and then it can do the following things with it. I'm not sure if that was a clear explanation.
I think it was, but just one thing that's
Yeah.
the pointer still refers to the same bytes as the array bytes. Basically the same numbers. It just uses a different path to access them. Or are those different instances from the moment you define the pointer? So if you change the pointer values, does this change the array values, or are these two different things at this point?
It changes the array values. So the pointer is, as I showed with this assembly, just the address of the entry of the memory where the array is. And if you make a pointer well plus something, then of course you can move in this array, but you will always be addressing memory that is located within this array. It does not copy that array at any point in time. So if we here let's make this a different number, 456, and make a few breakpoints. So if we now, so first it will be, I don't know, some small number, 3. Okay, then we make a step, we execute this access direct to the array, then we see that it of course changed it. But then if we access the pointer, then we see again that it also has changed the values inside the array, because the pointer really, as the name says, it points to memory, and this can be either memory which is allocated just as a big piece of memory, or it can be some more well-defined array. Okay, good. So that is that. So to continue with the pointer stuff, as said, you can. So if we go back to this example, if we write a line like this, the pointer here, let's make a breakpoint, will be referring directly to an address in the middle of the array. So here we can get this. So this is this address, and if we take a look on our array before, we can actually subtract those from each other, and it actually gives us the number 6, because it still knows the type. So as long as you have a pointer with a given type, if you add or subtract from numbers from it, it will always do that in the increment of however large your data type is. If you want to actually get the real number of bytes, then you need to convert. Actually, void should also work. I think, or it will complain. No, it will complain that doesn't know the type. You can always complain to convert to characters, because they have only 1 byte, and then if you do the subtraction, you get really the difference in bytes, however many there are. And I said other than that, you will get an increment. And for example, a use case would be here. What we could do, for example, with the pointers is that you can make pointer plus plus, and this will then advance you to the next entry of the array. So maybe write down an example. So again, int asterisk. Let's call it temp. Let's point it to the array, and then you can make. So we want to dereference it to assign a value. We want to advance it to give it a value, and let's say we make it 1, 2, 3, 4. So this way, first of all, it takes the value, it advances it internally, and it dereferences the value that it was before it advanced it, and you can access the array and assign new values with it. So probably more useful use cases would be when we take a look on control flow structures, where you can have loops and stuff like that, because then, for example, in a loop, you would use such you could use such a thing to go through an array. So maybe we should actually make an example right here. So so for example, instead of doing it like this, yeah, that sounds like a plan. We can make a loop. So in C++, if you want to create a loop, use the for statement. And yeah, but this kind of I'm thinking, because it moves us already to the control flow side of things. Yeah, but I think we can do it. So nah, let's do it later. So I will show you how to make loops later today. Now let's finish up with the pointer stuff first. Yeah, so we have this. I think that is pretty much all the important things anyways. You know how to take a pointer, know how the pointer works. Yeah, I guess in principle that would be all anyways. There is not much about pointers to be said, I think, that wouldn't have already been mentioned. I will upload a more well commented version of that file to the Moodle, so not this one, but one that somehow in a nice way shows all the different applications of pointers, and we can start with the next thing on our agenda, the different control flow structures, and then later during the lecture we'll take a look back on the pointers and how we can use them really nicely within loops to access different parts of, for example, an array. So let's minimize this and create a new project again. Zack. No, that was the wrong key. Create project. Okay, we call it okay, it's thinking. Okay, so oops. Some well, quick glance into flow control we already had when looking into how equations are evaluated, but now we will take a look on how to, in a more structured way, control the execution flow of your application. So let's start with some variables, because they are always good to have. Let's give it the value 10, and then maybe let's make another one. Oops, maybe a small r. Okay, so there are a couple typical control structures in any programming language which are more or less the same in a way across all the programming languages. The simplest way of doing something is just to tell the program code to jump to another location. So we can demonstrate it if we assign here the value 2, then we %d, add 2, just print the number on screen. So if we run this, it will just write down 2, but then what we can do is we can alter this program flow, this control flow basically, by telling the program to jump to a location, go to print. So we add a label that marks the location, and then we can use the label. When this is of course converted into machine code, the compiler just looks where this number would be, and then it enters the exact number here. So if we take a look in the decompiler, as soon as this thing starts, then you see that it's just jumping to some offset within. Actually, it even gives you the name. But if you, of course, remove this name showing, then you see that it is just jumping to a hard-coded address, or rather, actually, it should be jumping to an offset. This resolves it to an address, but we already had this nice website. Online decompiler. So if we feed here, why there are two jumps? Gosh. If we feed this into our, is it here, decompiler? Where did I say? Oh, that's the wrong one. This one. Then we see that it is really just jumping by a small number relatively to where it is right now. It just jumps by 8 bytes to the next instruction. It's quite interesting why it's jumping 2 times. That is not what we really need, but here it's just jumping 6 bytes. I really don't know why the compiler did that. It doesn't really make any sense. But what it wants to do is to just jump over this instruction to the print label here. So if you see the addresses, it's jumping to the same address. Why they did it twice, I really don't know. So the compiler, especially in the debug build, sometimes generates rather strange code. So we should probably disable some of the debugger features. This will, as soon as it finishes loading, remove some of this strangeness that is usually makes the code much easier to read. Yeah, but here it also did it twice. So now I just switched to the other architecture, but that didn't help at all. So let's go with just removing all the debug stuff. So general, this is disabled. Code generation. We don't want this. We don't want this. Somewhere here, not here. And what was it? This. We don't want this. Is that all that? Is at least a good start? Let's see if this will generate a more straightforward code. No, it's still doing that. I have no idea why it's still doing it. It's completely useless. It probably tries to align the program flow. So what it's trying to do kind of is sometimes to make the program run faster, although it should not do it in a debug build, is you want to align the memory accesses to a 32 or 64-bit boundary, because when the CPU is requesting requesting data from the memory, it does this in chunks of 32 or 64, and in some cases 128 bits at once. And if your data are split across 2 chunks, you don't see my hands. I should remove the background, but I will do it for next time. So if you do it in 2 chunks, then you need 2 memory accesses, and it is much slower. So the compiler might try to align the program such that every memory access will fall into this boundary, such that the CPU then only needs to perform 1 memory access. I guess they are doing it here, but they could use a non-operation instead. Anyhow, the idea is that we just can jump around this code, and then the result will be that we will still have the -1 in our variable. And the most useful thing at the beginning is that we would want this jump to be conditional, and as we have seen it with the equations, there are already a couple of internal CPU instructions that allow you to create conditional jumps. And in C or C++, you don't need to care about the instructions in detail. Instead, you can use the if statement, and then you just give it an equation. Let's say, for example, this must be equals 10. And if whatever equation, the equation can be arbitrarily complicated, is here. If it evaluates to true, so if it's non-zero, then whatever statement is placed after the if, it will be executed. So for example, we could make a now a go to printf, and in this case it will still go to printf, but if we then change the equation condition, it will in fact not do it. So if we say that we want this to be 11, then we will see that it did not execute this go to instruction. And generally what you can do with any with different control structures in C++ is that you are not limited to just having one instruction. You just can make a block, a code block with these curly brackets, and then however many stuff you have inside, everything will be executed if this condition is true. So if the condition is fulfilled. So let's take a look how this is implemented on the machine side. And here, let's move it slightly, and yeah, we don't need this either. So you see here it makes just a comparison between the memory address. So here is just RBP because it's the first variable. If the other variables would have plus something like here, and then it compares it well 0p, that's 11, yeah, with the hexadecimal representation of 11. And if this is so jump not equal, so if this is not so if they are not equal, then it will jump around this code, so it will jump up to here. Yeah, the addresses are correct. And if this would be true, then it would just continue execution down the path and then arrive at our goto, which, as I said, I have no idea why it is implemented twice. The second jump will never be reached, because at the first jump we can step through it step by step. Because wait, we failed in the other step already, so we need to make this 10 again so that it will be correct. Okay, again, so step, and then we are already jumping. So this second jump is just there because the compiler was, I don't know, too lazy to use a NOP instead or something like that. But the more interesting thing is, of course, that we can here not just have a goto, but we can here, for example, have a we can this make maybe +2 plus equals 2, and then here we can have this is equals 3. So and plus equals 1. So just for the demonstration, we can have here an arbitrary amount of code, and we can can have here another if with another code block and another and another and another. So these things are cascadable arbitrarily. But of course, what you also would maybe want to do is, assuming this is not true, to do something else. And there is this keyword else that does just that. If the condition is true, the one code block will be executed, and if the condition is false, another code block, I don't know, let's make something that will have the same result, then the other code block will be executed. And what you also can do is, if you have more conditions, you can use an else if, which basically is so in principle you can just put this into that. So let's say this is 11, this is then 1 plus 3, I don't know that, yeah. And then you could of course put more conditions into the next else, into the next else, and cascade this arbitrarily. But to make code more readable, you can in fact collapse this down to something like this. Semantically it is exactly the same thing as we had with putting the whole next if into the whole code block, but this makes just for a more readable code. So the idea is that whatever comes after the else, whatever statements come after this will be executed, and if the statement is a whole if, then the whole thing is the next statement. It doesn't need to be explicitly put into our own code block. And as said, we can have as many of those as we want. Yeah, 12 for example. And so in this case, if it's 10, it will do the first one, then the second. If this is not true, then it will check the next condition. If it's not true, the next one. and of course then it will fall into the else case if none of the conditions are met. Of course, you could also just don't have a default else case. This is also just perfectly fine. And as said, you can have here any arbitrary complex equation. If we have just single numbers like here, so if we have a simple comparison, there is another control structure that can be used. It is called a switch. And the idea, at least historically, is that such switches should be somewhat more efficient than just normal ifs. But I think nowadays this does not really matter. So the way this is written is you have your switch, and then you can define cases. So case 1, sorry, and then you write the value. So that was 10. Then you write double point, and then you write what shall happen in this scenario. So here we can really just replicate that. But there is a very important thing about this structure. Namely, if you add the next case, 11, let's say this was supposed to be that. And now we will step through it, and you will spot that something strange happens, which might not be directly expected. Okay, so we don't care for this breakpoint. We go to continue. So we are here. Okay, maybe I should make a better test case because this is not great. Let's make also the 12, and here, I don't know, 2 and 2. Let's put breakpoints everywhere, and let's start with the values 11, because if it like starts in the first case, that's kind of boring. So we see that it arrives, it automatically we don't see it because I should put the breakpoint here or somewhere else to be a good demonstration. Yeah, so we start here. We have here this jump table that it creates internally, and then we can make a step, and the next step, and the next step, and once it did what it did, it brought us directly to the case where we wanted. So let me disable this. So the case 11, then it will do our 11, but then what it will do, you will notice that it will continue the execution and fall through to the next case. And this is a very common source of programming mistakes as well, that this switch case structure, that a case always falls through to the next one and the next one and the next one unless you tell it to break. And this is now the actually correct code. So here we use break. And the reason why it falls through is because you might want to write code that, so you might want to use this switch structure, but have multiple values that will trigger the same case. So here, of course, the analogy to this would be here to make an equation out of that. This would be the same thing in principle, but it is often more useful to use it this way. So if you have, for example, some thing that does things based on a status code, and you may have many status codes for which you want to do the same thing. For example, you want to do one thing if it's a success, you want to do another thing if it's an error, and you don't care if it's error 1, 2, 3, 4, or 5, or however many you might different error codes have there. So there you would, for example, use such a structure. Of course, in the simple example, it's rather like you could have done it with a if, because if it's success, then you do, and else are all the errors. But let's say you have 2 errors that do one thing, 3 errors that do another thing. At this point, you would already need to start writing a lot of ifs and type more code. So you can do it this way. And you can also have a default case called default, well, obviously, which is just executed if nothing else, if none of the other cases is hit. And it has the same behavior that if the break wouldn't be here, the case 12 would fall through to default. And this falling through is not only useful if you just want to make this structure, but in fact you can use it in special cases to your advantage. So, for example, if you have a generic error case where you just want to abort, and then you have some special error case where you also want to print an error message, for example. So you would have all your errors that print an error message first. Then you would have here print my error or something. Oops. Doesn't matter. And then you would have then your cases that are all the cases which don't print an error message. But then you still need for both cases to make a cleanup. So if you would not have this fall through, then you would need to replicate the code from your cleanup case to your print error and cleanup. But this way you can just print your error and then fall through to the normal cleanup code. So that would be one simple example of where you would want this fall through mechanism to be used. And well, what else? You don't need to make a break at the last instruction, obviously, because this is there is nothing else to break from anyways. And in fact, in other programming languages like C#, for example, if you don't write break, it will complain and not want to compile your code. So they, in one way, wanted to be compatible semantically with C++. So they said, okay, you need to have a break. But then they wanted to avoid people forgetting, and they made it an error to not do it. So it's a strange decision. But in fact, you could in C# fall through to the case. You just need to write, I think, next, and then the label of the case you want to fall through. So it is doable. It's just not as pretty, or maybe it is also pretty. I guess that depends on your preferences. I would prefer less code than more, but well. So yeah, what else? You cannot have a label twice. When you're writing an if, in principle, you could just write something like this with the same condition, and obviously only the first one would trigger, and this one would never be reached. The compiler is not smart enough to warn you about this case. If, however, you would do the same thing here, it would just complain and refuse to compile. So you see here it's saying that the label is already used, and it even tells you where it is used. So this is another use case where it is good to where you would benefit from using a switch statement instead of an if, because it simply just allows you to be more flexible to find this error. Plus, it has this flexibility that you can go from one case to the next. With an if, you cannot really do it. With an if, you would need to that could be something for homework. That's a good idea. I will have to come up with some homework for you. I will probably think about something that you will maybe need to convert a switch statement to an if, or the other way around. Well, but it probably will not be today, since some of you are still working on the last homework. So I will have time to think up a well-formulated homework assignment. Let's look towards the other control flow structure, since it seems we are using the time today up quite fast. So well, we don't need this. Yeah. So the next so this is already quite powerful, because with this we can even make a loop. So for example, int e is equal 0, and then we have our label next, then we have a label done. Oops. Then we make here go to next. Then here we can, if I is equals 10, go to done. And here printf %d Abstand, i. I mean, super trivial, but this, for example, would be already a full loop, and at least conceptually, this already kind of is everything that exists that is used in programming languages. Conditional statements do if something is given or don't do it, or do something multiple times. In a second we'll take a look on a more nice way to write a loop, because this in C++, like in many other languages, we have special keywords to write a loop in a really nice way. This is just a let's say demonstration use case how you can write the loop. And the nice thing is that this in fact demonstrates, oops, what's wrong? Okay, demonstrates how a loop would internally be implemented. So when we then in a second take a look on a on a loop implemented using the appropriate keywords, we will see that internally it will be very similar to what we see here in terms of machine code that was generated. So when we start, we first have we have here a breakpoint we don't longer need. So let's go to the next one. Okay, so when we start first here, we are assigning a start value, for example, to a variable. Of course, we could have a loop with any other sort of abort condition. And as you notice here, probably also we could write any if. So we could also have an if e is equals. Oh, I forgot an important thing. Our loop will run forever because it's never changing I. We need to change I, obviously. Or in this case, increment it. Otherwise, our loop will never end. Okay, so again, so we start. Then we have a label which is not present. It is just an address. Then we have our condition. So here it is checking whether the condition is not fulfilled. So if it would be fulfilled, it would be go to done, but it is not. So when we step through it, we see that it's jumping here around this next go to statement. Then it's executing our printf, which prints a number as expected. Then here it increments our loop counter, and then it executes a jump. Here it actually worked fine. It just made one jump. I really don't know why here it again made two. It must be some alignment thingy. Anyhow, and the jump here to this address just brings us back to the beginning. So it is checking, and at some point, if we put a breakpoint here, at some point we made 10 iterations. Our I became 10, and now we can jump to the done address of done. So in this case, it's this address here, as we can see. And we are in the loop basically finished. And we can do the same thing with the for keyword. For let's make j is equal 0, e is well ungleich 10. So the condition in the for in a for loop is so it's initialized. This is executed once when we enter the loop. Then the next thing is it checks the condition. After it checked the condition, if the condition does not say abort, then it will do the loop body. So the loop body can be either a single line statement, or more often, a code block. In our case, it is not, but it could be. And after the code block has been executed, it then enters this last portion here where we have the I, does the incrementation, and then it goes back to checking, executing, incrementing, and then it repeats until this is not longer true. So until this will be 10, because if it is 10, then it is not true, and at this point it will jump out and finish the loop. So if we put a breakpoint here, we will see that in principle it did the exact same thing, maybe with slightly more code, but okay, so here we are initializing the thingy. Okay, it's, for example, it did not, like here it kind of showed us for every line which line is doing what. Here we just have the whole logic of this thing being put in one place. But if we step through it, we see, okay, we initialize the value, then we jump already to the test location. So here we make the comparison of our RBP8. Why is this a different address? Oh shit! I noticed on the addresses that something's fishy. I should have used J here, obviously. Now it should be fine. So, okay, we initialize the RBP plus C. Then, shit. The focus was again in the wrong window, so this is really annoying. Okay, now it should be fine. Now we should go by one line. Yep. So, and now it jumps to the test routine. Here it checks whether it is equal or not, and then it sees, okay, jump if equal to another address, but it's not equal, so it does not execute the jump. And here instead it will call our function. How function calls work, we will take a look probably in the next lecture or the lecture after that. Function calls is a bit of a bigger topic, so here we are skipping over it. Then we go to the last jump. Okay, I think the implementation is slightly different, because as you see, the jump here will bring us to the place here where we increment the pointer. So like we could actually write this as the other thing. That's a good homework assignment. That is probably that might be maybe today's homework assignment, unless you think that's too complicated for you. That you will need to tell me. But I think it should be easy enough if you have this here as a template. Anyhow, the point is we increment, we write down the value again to our memory. So this, for example, is something that if this would be a release build, might have been optimized out, so that it may be not saving the value back to memory for each iteration of the loop, but it would say, okay, let's just use one register for the loop counter. Iterated, incremented, so just use only the increment x instruction, and we also don't need to load it. That saves us even more time. And then once we are done with the loop, only then we save the value to actual memory. So this would be like one of the easier optimizations that one could came up with here. Okay, so then after we have made the test, we do the comparison again. Don't jump, and then of course at some point we will do the jump to this address, so to here, and well, we do. So if we play, it will just bring us just to the next breakpoint. And in C you have in fact a couple more types of loops or keywords that allows you to implement a loop, but they are kind of just simplified versions of this for sort of thingy. And what I wanted to show you earlier with the pointers, let's again create an array. Int my array of small a is like... Oh, there was one thing I forgot to tell you when I told you about arrays. When you initialize an array with numbers, you don't need to put a number here. So if you initialize an empty array, then you need to write down how big it will be. And this number is, it must be, so you cannot use a variable here. You could use maybe a const variable, but a const variable is just a placeholder for a real number. But if you are initializing it, then you can just make it empty, and the compiler will just count the elements here and then know what number to put in. This is quite handy. And of course, if you would put here if you put a larger number, we already saw that it will just be padded with 0, but if we put a smaller number, then the compiler will complain here. You see it's red that we don't have enough space. That's right. But let's create our pointer. So int asterisk pointer is equals array. And then inside our loop, we can... Actually, we could put this as our initialization command. Then we can make asterisk pointer is unequal 0. Actually, we don't. This unequal 0 is almost always not needed, because the definition of something being true is that it is not 0. But for better pedagogical value, let's write it down. And now we just make pointer plus plus incremented, and now can here in our loop get the value from pointer, and this loop will run until it encounters the last element, which is 0. If the 0 would be in the middle, it would abort early, but it's where it should be, so it's fine. And this is quite a nice way to use pointer, so you can really advance if you have some workload or some task or a string of characters or something in the shape of an array. As long as you can define a proper abort condition, then you can this way increment through your array, and yeah, that is quite nice. So let's run it quickly. Well, as you can see here, it is very simple to the other loop. Of course, here instead of an increment instruction, we have a add 4 because it's the plus plus increments the address by the size of integer. Other than that, it should look pretty much exactly the same as here. We also here see the initialization, which is quite it takes actually quite a lot of memory to do because it is always using 32-bit numbers, so it's wasting some memory accesses here. If we would compile this for ARM, I think sufficiently short numbers can be encoded into the opcode itself, so we would probably only use 4 characters. But well, that is something for later. So we can just run the loop here, and it just wrote down the additional values starting from here. It didn't write down the last one. Yeah, simply because the way this works is that if this condition is no longer true, then it will abort without executing anything inside. And what you also can do with loops is you have 2 special keywords. One is let's make another loop for. Let's make an endless loop. So we make here a loop which has no abort condition. So an empty condition basically in this case means just do forever. But we want probably to abort something still, so we can write here let's say int k is equal to 0, and internally we can have first an if k plus plus is equals I don't know by then break. You already saw the break keyword earlier with the switch statement, but it can also be used inside a loop, and the break will break out of whatever loop it is currently in. If you have multiple loops concatenated, so if you have a loop which contains another loop j, the break will only break you out of the loop you are in currently. There is no keyword to break out of 2 loops at once, but you can of course use the goto statement to achieve that. So if you would want to break out of 2 loops at once, you would just, let's say, make some label and then just write go to breakout. So this way you can really jump out of 2 or however many loops you might have. But if you are just have 1, you can use this break command. Or another keyword that you also can use when you are inside a loop is the continue. So let's say we have we start with this, then we have something. Okay, let's do maybe with some prints. Printf k, and then printf k plus 10. And let's say we don't want to do it always, so we could have if k is unequals to, then continue. And continue, what it does is it aborts, it stops the loop execution in this point and returns back to the beginning. So we can put a breakpoint here and there and there and take a look on it. Since we only have 3 iterations, wait, the condition is wrong. K should be smaller or equals 3, or else this thing will abort immediately. Okay, so oh, was I wrong? No, it was if. No, sorry, k was right. Yeah. So the continue basics just is a jump to the begin of the loop to, in this case, this address. So if we go through it step by step, we just arrive at the beginning again, and then we can do something. Okay, we don't want to take a look inside this, we just go over it, and since the condition is no longer true, it then passes again here. So if you have a loop and you are doing some stuff, you can at any point of the loop's execution trigger the execution of the next run of the loop and not have whatever comes after it executed during this iteration. Comparably to the break keyword, the continue keyword only affects the current loop you are currently in. If you would want to do such a thing over more than one level of loops, you would need to just use a goto instruction. And of course, if you put a switch statement inside the loop, then you cannot use the break instruction from the switch. But the continue instruction, since there is no continue defined for a switch, would still work for the outer loop. Yeah, so how to break out of two loops we already said. So now let's take a look on the few other sort of loops that are available in C, in the C language. So one is a normal so-called while loop, which basically is just the condition of the for loop without anything else. So a while loop, so this must be true, is pretty much equivalent to such a thing. This is semantically the same thing, just that you don't have a place for something that will be done before, but you can just put it in front. So you have int, what was it, k l equals 0. Then you have l is kleiner, 10, and then l plus plus. The important difference is that the continue will of course execute your did we forget this? No. Will of course execute your incremental function. So let's this make just being k, and this put the k here. So if you continue, then you will increment the k as well, and yeah, it is useful, but of course you could have your L being here. But then of course the difference is that when you enter the for loop, you don't do the first k, you just do the initialization and the check, then you do your body, and then you do k. In the while loop, you would always do your first go through if you would do it like this. If you want the incrementation to be always caught by the continue statement. So this, yeah.
Just one short question. The break, you said
Mhm.
only breaks one, right?
Yes.
But didn't you intend to use the break here to break out of the infinite for loop?
Well, the loop is infinite. There is no condition here.
Yeah, you're right. But does this break out of the for loop? Because for me it looks like it only breaks out of the if loop. But does it break the if and the for here?
There is no break defined for an if.
Okay, so the break only breaks the for loop.
Yes.
The if doesn't have a break. Okay.
Yes.
Obviously. Okay, thank you.
Yeah, you're welcome. One note at this point for the recording: I have put the two last lectures on YouTube. Maybe you have seen the link, and there is only my voice and the screen. So sometimes it probably sounds strange when I'm having discussions with myself on the recording. Just so that everyone knows that. Yeah. Anyhow, okay. So this much to the while loop. It is, as said, quite similar. Just that there's a slightly different behavior with regard to when or how to put your loop increment. Obviously, the loop does not really need an increment, so you could have a endless loop, and then check, for example, query a function that queries some operating system value and then exits, or that queries a variable which can be incremented by another thread. So you can have different break conditions. Here we are just using always variables because this is a simple enough case. What you also can do with such a while loop, if you want to make it slightly more like a for loop, you can just put your increment directly into the condition. Of course, then you have to take into account that once you enter here, the L already will be incremented. So that here we would start with L1, while here we would start with k still being 0. So there are ways to make them more similar, but at the same time, it's not really possible to make them completely identical. That's why there are different keywords for that. And the last type of loop that we have in C or C++ is the do-while loop, which looks like this. Let's reuse L. 220. And the difference here is that so the for and the while loop will check the condition before even executing their body the first time. So if you have if you are not initializing L or K within your loop but take the variable from somewhere, you could have a scenario where the variable already has a value which would make the loop not execute even a single run. With a do-while loop, it is different because it will always execute the body, and only then it will do the first checking whether it should abort, which is also quite useful in certain scenarios. So if you want something to be always executed at least once and then maybe repeat it again, and you know that the first test would always say do it anyways, then you can save a few minor instructions and CPU cycles by using this do-while loop. So it is, as said, it is very, other than that, it is very similar. And this would be all the types of loops that you can use in C++. Is there anything else about loops to be said? Not really. Are there any questions at this point? Okay, so we had all the questions while we were talking about the things. This is also good. So let's think about some homework. I think that is a reasonably easy homework. To create, let's copy those things. Is it worth it? Yeah, that is reasonably easy. That should be reasonably easy, yeah. I'm thinking, can we do this? This already behaves quite similar. There is just really one small difference in behavior with regard to the order of operations. But if you step hint it really should be quite easy, because as said, you will only need to change the order of a few things and add one additional jump instruction, go to instruction in this case. So I think that is a good homework at this point. For the next lecture, what will be next to the next lecture? Pointers we already had, flow control. So for the next in the next lecture, we'll take a look on structures and function calls, and that should be more than enough for the next lecture, I think. Since I completely forgot to make the 15 minutes break, it wouldn't probably be wrong if we finish today earlier.